determine the most accurate correction factor for outside exposure according to the 2002 National Electrical Code, specifically Table 310.16, firstly refer to the local building codes or ordinances of the municipality. These local regulations might already specify a particular correction factor tailored to the area, taking into account the specific climate and other pertinent local factors. In the absence of explicit local guidance, carefully consider the following environmental factors that influence conductor temperature and ampacity. Firstly, the latitude and altitude of the location. Secondly, the geographical setting of the installation. And thirdly, the annual temperature range experienced in that location. Consider a location with a latitude around 33.5 degrees north and an altitude of approximately 1100 feet above sea level. This location is situated in a desert characterized by hot, dry summers and mild winters. It experiences extreme temperature variations, with summer highs reaching over 115 degrees Fahrenheit and winter lows potentially dipping below 40 degrees Fahrenheit. Based on these factors, a suitable correction factor for outside exposure from Table 310.16 of the 2002 National Electrical Code is 1.25. It's crucial to understand the additional applications of this correction factor. Beyond roof or exterior wall locations, the correction factor for outside exposure should also be applied in several other scenarios. Firstly, attics. Attics are generally not considered enclosed spaces and are often subject to outdoor temperatures. Secondly, direct burial applications. Conductors that are directly buried underground are also exposed to similar temperature variations as those found outside. Thirdly, raceways exposed to direct sunlight. Raceways mounted in the exterior of a building or otherwise directly exposed to sunlight are subject to significantly higher temperatures than those installed in shaded areas. Fourthly, conduit bodies located outdoors. Conduit bodies that are not enclosed and are exposed to outdoor conditions are also subject to temperature variations. It is important to note that the correction factor is not typically applied to conductors installed inside enclosed spaces, such as within interior walls or inside conduit runs that are shielded from direct sunlight and extreme temperature variations. Remember that Table 310.16 provides ampacity ratings for conductors based on a specific set of ambient temperature conditions. When the actual ambient temperature differs from these specified conditions, the ampacity of the conductor must be adjusted using correction factors. These correction factors are multipliers that are applied to the ampacity rating to account for the effect of temperature on the conductor's ability to dissipate heat. The higher the ambient temperature, the lower the ampacity of the conductor. Conversely, the lower the ambient temperature, the higher the ampacity of the conductor. To accurately apply these correction factors, it's essential to have a clear understanding of the ambient temperature conditions in which the conductors will be operating. This may involve taking temperature measurements at various locations throughout the installation and over different times of the year. The correction factors in Table 310.16 are based on specific insulation temperature ratings. These ratings indicate the maximum temperature that the conductor's insulation can withstand without degradation. It is crucial to select conductors with insulation temperature ratings that are appropriate for the ambient temperature conditions in which they will be installed. If the ambient temperature exceeds the insulation temperature rating, the insulation may degrade, leading to premature failure of the conductor and potentially creating a fire hazard. In addition to temperature correction factors, it's also important to consider dirting factors. Dirting factors are applied when multiple current-carrying conductors are bundled together in a raceway or cable. The heat generated by these conductors can raise the temperature inside the raceway or cable, reducing the ampacity of each conductor. Dirting factors are specified in the National Electrical Code and must be applied in accordance with the code requirements. When applying correction and dirting factors, it's essential to follow a systematic approach. Firstly, determine the allowable ampacity of the conductor based on its size and insulation type from Table 310.16. Secondly, identify any applicable temperature correction factors based on the ambient temperature conditions. Thirdly, identify any applicable dirting factors based on the number of current carrying conductors in the raceway or cable. Fourthly, multiply the allowable ampacity by the correction and iterating factors to determine the adjusted ampacity of the conductor. The adjusted ampacity must be equal to or greater than the calculated load current for the circuit. In some cases, it may be necessary to increase the size of the conductor to compensate for the effects of temperature and bundling. It's also important to consider the voltage drop in the circuit. Voltage drop is the reduction in voltage that occurs as current flows through a conductor. Excessive voltage drop can cause equipment to malfunction and can also reduce the efficiency of the electrical system. The National Electrical Code specifies limits on voltage drop for both branch circuits and feeder circuits. To minimize voltage drop, it's important to select conductors that are large enough to carry the load current without excessive voltage drop. The length of the conductor also affects voltage drop. The longer the conductor, the greater the voltage drop. In long circuits, it may be necessary to increase the size of the conductor to compensate for the effects of length. When selecting conductors, it's also important to consider the type of load that the circuit will be serving. Different types of loads have different current characteristics. For example, inductive loads, such as motors, can draw a large inrush current when they are first energized. This inrush current can cause a voltage drop in the circuit and can also overheat the conductors. To accommodate the inrush current of inductive loads, it may be necessary to increase the size of the conductors or to use a motor starting device. It's also important to consider the harmonic content of the load current. Harmonic currents are currents that have frequencies that are multiples of the fundamental frequency of the electrical system. Harmonic currents can cause overheating of conductors and equipment and can also interfere with the operation of sensitive electronic equipment. To mitigate the effects of harmonic currents, it may be necessary to use harmonic filters or to select conductors and equipment that are rated to withstand harmonic current. The National Electrical Code provides detailed requirements for the selection and installation of conductors. It's essential to follow these requirements to ensure the safety and reliability of the electrical system. The National Electrical Code is updated every 3 years, so it's important to stay current with the latest edition of the code. The National Electrical Code is a comprehensive set of standards that covers all aspects of electrical installations. It's a valuable resource for electrical professionals and anyone else who is involved in electrical work. Understanding the National Electrical Code and its requirements for conductor selection and installation is essential for ensuring the safety and reliability of electrical systems. Correct application of temperature correction factors is just one aspect of ensuring electrical safety. It is critical to consider all aspects of the electrical system design to ensure compliance with the applicable codes and standards. Failing to apply the appropriate correction factors can lead to overheating of conductors, which could damage the insulation, potentially leading to short circuits, ground faults, and ultimately, electrical fires. This can result in significant property damage, injuries, and even loss of life. So, always consult the latest version of the National Electrical Code and local amendments, and consult with a qualified electrical engineer or inspector to ensure your installations are safe and compliant. Also, remember that while a correction factor of 1.25 might be suitable for the given scenario, this is just an example. The actual correction factor will depend on the specific temperature conditions, conductor insulation type, and other factors as outlined in Table 310.16 and related tables in the NEC. Always perform a thorough evaluation of the specific installation conditions to determine the appropriate correction factor. Finally, always ensure you have appropriate training, qualifications, and safety equipment before working on or near electrical systems. Electricity is dangerous and should only be handled by qualified professionals. Remember that this explanation is for informational purposes only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer or inspector before making any decisions about electrical installations. The integrity and safety of electrical systems depend on a thorough understanding and correct application of the National Electrical Code. Therefore, continuous learning and professional development are essential for electrical professionals.